literature called image decomposition.
Thank you, Mr. Chairman. Ladies and gentlemen, an image decomposition approach to validation is what I'm going to present. The author, I'm Erwin speaking here, and the co-author is Ian Patterson, who happens to be here in the first row. I will talk about, of course, validation of numerical models. That's the conference about. And when we talk about validation, this always includes something experimental to compare with. So I'm focusing on strain measurement here, say in 1D, 2D and 3D space. We then focus on data compatibility, so how can you compare data-rich maps. And the tool we suggest here is image decomposition. It's also good to have a quantified parameter to say how good the model is. So how can we quantify the model quality? And I'm going to end with a conclusion, and you will see more presentations this morning along the line. So if you think validation of numerical models, I'm pretty much focused today on simulation of structural components only. And their strain or stress fields are normally used to predict the damage or to see the performance that you have been planned in your specimen. And validation here is meant to be by comparison to experimental data. I've wondered how many experiments have been presented here. I came across a few only. So I think this is maybe an essential part once in the flow of a numerical model simulation. Now, while you can model your structure quite easily in 3D today, you hardly get any volume data for a loaded structure, right? So what you can do is here exemplify. Maybe you just get a computed tomogram of a structure, a torsional cylinder here, and you can have statistics about the flaws and size of these flaws through the thickness of this multi-layered structure. But this is just a static one, so there's no load on it. And if you want to exert load here, it's normally a trouble to get into a computed tomogram machine. So therefore you hardly have these strain or stress fields inside. The only thing that's left actually is surface strain data. Surface strain are accessible. You can do them in situ and under defined loads, depending on your apparatus to load it. And you can easily use point measurements, like introducing strain gauges here, rosettes in several places. And then, of course, you get a single point measurement here. The experiment we have is a saw notch residual stress release experiment. So we gradually increase the notch here and observe. This is just one of the rosettes. You observe the evolution of the strain in 3 different directions. Well, this can give you some hints. However, you don't know exactly, because residual stress, this is an injection molded component, is not quite clear where they should appear and to what size. So you see, we go something like to 600 microstrains here in compressive. So a better solution would be to have full field data available. So what we do is an optical technique called speckle pattern interferometry, and I'll show you here just part of the view here. So this is now a whole area that you measure instead of 3 single points. And you get for every step in your saw notch, you get X strains, Y strains, and shear strains. And you can do that for every step, and you have much more insight into the process. You see here, at the location maybe you wouldn't expect quite severe Y strain. So now we have surface strain data. And the question is, how can I use that for validation? So the topic would be faithfulness and validation here. I'm sticking to the International Vocabulary of Metrology definition, which includes that validation is the provision of objective evidence that a given item fulfills specified requirements adequate for its intended use. Well, this sounds like a lawyer's statement, isn't it? So you have to read it 3 or 4 times to get really the message. Let's abbreviate it into engineer's term. It should be fit for purpose, right? So we have an intended use, which is the purpose. It should be fit, that means it should fulfill the specific requirements. But we also need to provide evidence for that. We just cannot claim it, right? So what's the intended use of modeling? I would say it's a faithful representation of a real-world situation. Otherwise, the objective in the evidence is not there. So the question is, how fit is the model? Can you quantify this faithfulness? And we suggest that objective evidence is provided by the comparison to a representative experiment. Representative in the sense that it should include all the essentials you build into your model, otherwise you cannot test against it. Just to say a word, it's actually applicable to all kinds of data fields. I'm just going to strain or stress here, but of course you can use temperature fields or flow fields or whatever you like. So the methodology itself is not related to strain at all. Again, going to the vocabulary, if we do validation by data comparison, how can we actually make 2 data fields compared? Now you find this compatibility definition for 2 sets of measurements. So we have red dots and blue dots for the same measurement. And now the question is, are they compatible? Is this the same measurement? Is this the same level of whatever the measurement is? And the simple, straightforward way is you take the difference of any pair here, for instance this pair, from the blue and the red one, and it should be smaller than some chosen multiple of the standard measurement uncertainty of that difference. So this is the set 1, set 2, you pick any n and m, and it should be smaller than the uncertainty of your difference, and you may choose this kappa. So it's a choice here. It's nice, isn't it? You can choose on how good you expect your compatibility to be. However, okay, first, this is kind of a distance measure, right, for 2 points. It's just measure the separation here. And the chosen multiple is kappa, but it's only a single point criterion. So you have a bunch of measurements in red and a bunch of measurements in blue, and you just pick all the differences, and all should be smaller than a given amount here. But it's only a single point. However, you can also say, well, if I only have 1 point each in red and blue, this is sufficient. And what's the difference if you have a data field? Simulation and experiment, in our case of validation. So we could say, well, at least we need 1 value for each point, but of course you can also use clouds in each point here. So assume we have an n-dimensional vector written for the data, so we have a difference for m equals 1 to n between the strain measured with the optical method and compare it to the strain provided by the finite element modeling. Of course, the overall difference, you could be tempted to just use the root mean square. So this would be a useful measure eventually, but it doesn't qualify for a compatibility criterion. One of the reasons, of course, is if you have large uninteresting areas of zero or zero deviation, that brings down your RMS, but doesn't tell you more about the quality of your model, because normally what's going on is a location with high stress concentration, for instance. So this is not the whole story. I talked about endpoints and suggested that there is an endpoint comparison possible. But if you look into here a strain field on a curved surface, you will have different grids for the FE mesh. I just put the centers of the triangles here in black. And you have a different grid in red here from the camera system of your optical measurement. So what you see here is just a an XY view from top on the center of this distribution. So you see there's a mismatch here between the black ones and the red ones. And so if you want to do a point-by-point comparison, you need to bring those together. So you say, for instance, I take the FM grid as the master grid. So what you do is you interpolate your camera data in red here, normally the linear combination here, to get a single point measurement there, which is quite a tedious task. And I doubt that it's bringing too much more information than if you use another approach. So how can you obviate this explicit point matching? Now, a simple solution by, well, let's say if you're a student, you just try out things. You would say, well, I have an image output provided on my FEM. So if I do an image output, I get a grid which is not the same as my optics and it's not the same as my FEM, but it's a regular grid anyway. So you can do just an image here. That matches your data to a regular grid. Of course, it's also interesting to use the original data array, but that can be very skew and very irregular space. But what we suggest actually is you should parameterize your data, but in a unique way. All of you know about polynomial fitting. You must be careful, that's not unique. Because normally if you just do a normal polynomial fit or an image moment, so to speak, for a 2D situation, and the coefficients will change if you increase the order, because they are not unique. If you apply Fourier transform, on the other hand, this is unique, because all your base functions in frequency space are orthogonal. So what we suggest actually is a technique called image decomposition, where we do not use image moments, but we use orthogonal decomposition of the image. And then we have image descriptors available, which we can use for the comparison step. So this is I'm trying to well, maybe first I should explain before, I don't know where this pops up. So we can assume a set of orthogonal functions tk, where orthogonality here in a discrete version is the sum over the same points in a camera, say, in this side. If k and m are not the same order or not the same number of functions, then they will not give anything. If they are the same, they will give an amount to rho k. So you can do that on both spaces. You can do that in the image space for your camera data, and you can do that in your FEM space on your grids. It's always possible to find such functions. For a comparison, however, it is very important that you use an equivalent decomposition. It doesn't have to be the same grid. It doesn't have to be a point-matched grid. But it should be equivalent in a sense. You cannot use a Fourier decomposition in one space and orthogonal polynomial decomposition in the other. So you can express your strain data in the camera field by a linear combination of those orthogonal functions, and you can do the same here in the FEM space. Of course, we only gain something if you can truncate the series. Let's see what it works here. Well, near to. This is just a series of orthogonal polynomials called Chebyshev moments. They are polynomials, that means that you can see this is a fourth order in x and y. So you can construct all these. They are defined on a rectangular grid, but they are orthogonal also in the sum sense, not only in the integral sense. So it's a discrete polynomial. Sometimes we ask, is it possible just to use image compression instead of image decomposition? And the answer is, well, not quite so. Because if you do an orthogonal decomposition here into a linear combination of these base functions t, then it's the space actually where you define your grid defines the basis functions. And the basis is independent of the image content because you use it to decompose the image. Right? Whereas if you do, for instance, a principal component analysis of your image, you will diagonalize your image and get a similar orthogonal decomposition. But the trouble is here, it's the image itself, when you diagonalize it, that will define your base. So if you have two images that are different, of course you will get a unique decomposition here, but the base functions bm here are completely different. So you cannot just use the coefficients to compare because they are really linked. So the sigma m are the diagonal components of this S matrix here. So if the image content defines the base functions, it's different for each image, and you cannot interpret the individual components or a difference thereof between this space and that space. Okay, here's an example of an image decomposition. This is a FE result of a vibrating membrane. This is a speckle measurement of the same. What I showed here is actually this mean square residual after image reconstruction. So you start with the first largest moment and then you go in sequence to lower moments. And you see the red curve here is the FEM, this image. So it converges very rapidly, and after maybe, well, 20 or 15 even numbers of polynomials, you will have a perfect match. Whereas if you do the same thing for the experimental side here, it drops quite steeply as well in the beginning, but it levels off. It levels off because we have experimental noise on it. In this case, it's dominated by speckle noise. So that means your image decomposition cannot be better than that. Even if you go to 100 or so moments, you wouldn't gain anything anymore. So in this case, actually, it would be sufficient to compare, say, up to the 20th order and see how good they match. In brackets, I don't know how you do your simulations, but I know people that have always these very smooth ones because they know for sure to 10 places after the comma how good their material constants are. But of course you could also introduce scatter here by introducing clouds of or a redoing of the simulations for different input parameters. And then it would not go to zero strictly, it would also level off somewhere. Okay, so what's the methodology to compare these data fields then? So because we have originally this difference in every point, if we have point matching, we replace it now by a difference in the coefficients only. I know the base function is the same, so I know these coefficients describe the same type of content in the image. And that means instead of having 10 to 6 or something matched points, I will have only 10 to 2. Right. Coefficients AK and BK have the same dimension as the strain, so we really compare strain values here as well. And of course, you need the identical type and order to compare. Now, how can we visualize this compatibility? We suggest actually to do just a correlation plot. Right? So you have on one axis the FEM coefficients, the other axis will give you the experimental coefficients, and in an ideal world they would scatter around the 45 degrees line. Right? Because we have experimental uncertainty, we will probably need to define an acceptance band, and here comes the choice again. You can choose actually how good that will be. Acceptance band is chosen in multiples of measurement uncertainty, for instance 2 times, 3 times, as you like. But the measurement uncertainty is increased in our case by decomposition uncertainty. You have seen if you have enough components, the uncertainty of the decomposition is more or less the speckle uncertainty, so this isn't contained here already, but in other situations there can be an increase here. You probably need calibrated instruments to do this exercise. Now the width of the acceptance bands governs the confidence in the model. You could always allow a large band and say, well, my model is fine. But large bands means you're not really interested in the details. So the choice of this multiplicator and the acceptable measurement uncertainty is something a strategic decision to take. And if you want to reduce these, this normally increases the cost of the experiment. 2 words of warning: you should use the same area of interest in both experimental and simulation, because you have an offset. You will have corrections in your coefficients given by the gradient in your shift, for instance, of the areas. And you should properly normalize the image descriptors. As I said, we do not have the same number of points, so you should do a proper normalization in both in the optical part and in the FEM part. So for instance, you would like to have the first component to be something like the average strain. This would turn out then that your normalization coefficients is 1/n, the points that you have in optics or in FEM. Okay, I hope I could motivate the use of full field surface strain data for validation. I treated model validation actually an analogy to metrological compatibility, and we suggest to use image decomposition for reducing the data of the full field. We suggested this criterion to quantify model quality. You could increase the band and see how large it has to be for a good match. And the whole procedure is actually described now in the CEN workshop agreement, so you find that online. I have the reference here, if you like. We acknowledge funding by the European Commission under the FP7 for this project called Vanessa. Thank you very much for your attention.